Hey, this is day 2 of gas laws. We're going to do some gas law calculations using Boyles, Charles, and combined gas laws. I have put, use your pause button as you need to, but I've put down Boyles Law. I've defined all the laws on here, so you can do that or you can go back and do it yourself. It's up to you looking in your notes. So I'm going to do just one in each of these. For Boyles Law, we're going to use Boyles Law. Boyles Law, the formula for Boyles Law is P1V1 equals P2V2. For the same amount of gas at a constant temperature, there's an inverse relationship between pressure and volume. So this is my formula. I find the variables within my formula. Volume does not have, it can be either liters or milliliters as long as both are either milliliters or liters. They can't be mixed. They have to be the same thing. And same with the pressure. The pressure can be in atmospheres, millimeters of mercury, whatever you choose, so long as they're the same. So I'm going to do number 3. It says a gas has a volume of 720 milliliters. So there's my V. Calculate the volume. So I'm looking for a volume also. Calculate the volume of gas if the pressure is changed from, that's P1, from 140 kilopascals to 650 millimeters of mercury. So here's the deal. These can be either one, but they both have to be the same. It could be either kilopascals or it could be either could be millimeters of mercury. It doesn't really matter as long as they're both the same unit. So I prefer millimeters of mercury, so I'm going to change kilopascals. I'll do that work right here. 140 kilopascals. We're going to do it as dimensional analysis. I'll disco down the unit and put kilopascals in the denominator. And I'm going to use the conversion that I learned last time. There is 101.3 kilopascals and 760 millimeters of mercury. These are two equivalent units. Okay, so this is going to allow me to change from kilopascals to millimeters of mercury. 140, let's clear that. 140 times 760. And I divide that by what's in the denominator, 101.3. So it looks like 1,050 millimeters of mercury is my second pressure. Or I'm sorry, my first pressure. There we go. So I list my variables. P1 is going to be 1,050 millimeters of mercury. P2 is going to be the 650 millimeters of mercury. V1 was 720 milliliters, and V2 is my unknown. So I'm going to plug them into the formula. P1 is 1,050 times V1, which is 720. Set that equal to P2, which is 650, times V2. So I'll multiply these two together and divide by 650. 1,050 times 720 divided by 650 gives me my V2. My secondary volume is 1,163 milliliters. So let's check sig figs here. It looks like there's 2 because there's 2 here, 2 here, 2 here. This thing has to round to 2 sig figs. There's 1, there's 2. So the 6 will round that up, and these 2 become zeros. So using significant figures, my final answer, 1,200 milliliters. All right. So we'll do number 9 down here, Charles Law. Charles Law says at constant pressure, there is a direct relationship between volume and temperature. The formula here is V1 over T1 equals V2 over T2. Again, as long as the units are the same, it doesn't matter what the units are. Although, yeah, just kidding. Although temperature does have to be in Kelvin. That's a definite. All right, the temperature inside my refrigerator is about 40 degrees Celsius. If I place a balloon in my fridge that initially has a temperature of 22 degrees C and a volume of 0.50 liters, what will be the volume of the balloon when it's fully cooled by my refrigerator? Wow, that was a mouthful. So I need to change 4 and 22 to Kelvin. So remember that it's just Celsius temperature plus 273. So 4 Celsius plus 273 gives me my first Kelvin temperature. Or actually it's my second Kelvin, but we can just label them 277 Kelvin. Need to change this 22 also. So 22 plus 273 gives me 295 Kelvin. 295 Kelvin. It says that it's initially 295 Kelvin and half a liter. That's my, not P, that's my volume and temperature. V1 is going to be 0.50 liters. T1, my initial temperature, 295 Kelvin. V2, my second volume is what I'm looking for. And my second temperature, we found 277 Kelvin. So I'm going to plug these variables into my formula. I don't know why I'm at 50, so it's 0.50 over 295 equals V2, I'm just going to use that as my variable, my x, my unknown, over 277. So the way we solve these problems is we cross multiply and divide. So I cross multiply these, 0.5 times 277, and I get 138.50. Cross multiply these. Set that equal to 295 times V2. And then I divide. So cross multiply and then divide. And divide both sides by 295. My V2 is divided by 295. Gives me 0.4. Ah, it's a big number. Let's see, how many sig figs can I have? I can have 2. So the 4 and the 6 are my 2 sig figs. That 9 will round that up to a 7. So my final answer is 0.47. 0.47 liters. All right, moving on to page 6. Gay-Lussac's law says that when volume is held constant, there's a direct relationship between temperature and pressure. My formula here can be similar to the other. P1 over T1 equals P2 over T2. And I'm going to do the same thing. I'm going to cross multiply and divide. Pressures have to be the same unit. Temperatures must be in Kelvin. Number 15 is the number I'm going to do. A cylinder of oxygen has a pressure of 750 millimeters of mercury and a temperature of 25 degrees C. To increase the pressure to 355 kilopascals, what must you change the temperature? To what must you change the temperature? Okay, first thing I'm going to change that to Kelvin. 25 plus 273 gives me 298 Kelvin. Ooh, 298 Kelvin. This time I'm going to change to kilopascals. Okay, so I'm going to change 750 millimeters of mercury to kilopascals. I'll work right here. So 750 millimeters of mercury. Disco down the unit. So I put millimeters of mercury in the denominator, and I put kilopascals in the numerator. Then I use my conversion factor. I know that there is 101.3 kilopascals is equal to 760 millimeters of mercury. So that'll cancel. I'll get kilopascals then. 750 times 101.3, and then I divide by 760. 99.96. So 99.96 kilopascals. So that's what I'm going to use right there. So 99.96 kilopascals. Alrighty, so let's put the variables that I have now into my formula. So cylinder has a pressure of this and a temperature of this. Okay, so these are my initial variables. So P1, 99.96 kPa. T1 is 298 Kelvin. P2 is 355 kilopascals. And then my T2 is the unknown. So I'll plug these numbers into my formula. 99.96 was my P1 over 298, which is my T1, equals 355, that's my P2, divided by T2. Cross multiply and then divide. So I'm going to cross multiply these two numbers. Put it over there so you can see. 298 times 355, and then I'm going to divide it by 99.96. T2 is 1058 Kelvin. That's hot. So let's see how many sig figs can I have. 2, 3, 3. So I can have 2 sig figs. 1058, there's 1 sig fig, 2 sig figs. The 5 will round that up to a 1. So my final answer is 1100 Kelvin. Again, pretty hot. Alright, so combined gas law is kind of neat. It combines all the variables. P1 V1 over T1 equals P2 V2 over T2. And if you know, this is a neat formula because if you know, let's say I want to calculate Gay-Lussac's law. I know that Gay-Lussac's law, volume is held constant. So if you take the combined gas law and you cover up the V's, look, you have Gay-Lussac's law. If you know that Boyles Law holds temperature constant, look, P1 V1 equals P2 V2. It's pretty neat how that works out. Okay, so let's do number 19 here. A gas occupies 5.8 liters at standard temperature and pressure. To put the gas into a smaller 0.75 liter container at 4 atmospheres of pressure, what must the temperature be changed to? Okay, so that is going to be my V2, and that's going to be my P2, and I'm looking for T2. I don't know what that is. All I have is 5.8 liters at standard temperature and pressure. I did this one on purpose because standard temperature and pressure gives me a temperature and a pressure. My P1, V1, T1. So I'm going to list out these variables and show you. My pressure, what's standard pressure? Standard pressure is 1 atmosphere. Remember that was in your notes, standard temperature and pressure. So if you've got it at STP, standard pressure is 1 atmosphere. I have my volume, 5.8 liters. How about my T1? What's standard temperature? What is it in Kelvin? It's 273 Kelvin. Okay, that's useful. I do love that. It's useful. So I've got my initial variables, and so let's see what else we have. We have P2, 4.0 atmospheres. V2 is 0.75 liters. And then my T2 is my unknown. So I'll put these variables into that equation. Okay, P1 is 1 atmosphere. V1 is 5.8 over T1, which was 273 Kelvin. P2 was 4. V2 is 0.75. And I'm looking for T2. Okay, before your brain starts to hurt, we're going to cross multiply and divide again. This time, though, I'm going to cross multiply this times this times this. Still cross multiplying. So 273 times 4 times 0.75 gives me 819. Then I'm going to cross multiply this way. 1 times 5.8 times T2. 5.8 times T2. Then I divide. Divided by 5.8 because I want to get T2 by itself. So my T2, what is my T2? 819 divided by 5.8, 141 Kelvin. 141 Kelvin. How many sig figs can I have? 2. 141 will round to 140 Kelvin. Okay. Page 6. All right, so page 7, at the top, we've got Dalton's Law partial pressure. This one's really neat and pretty easy. The total pressure of a mixture of gases is the sum of its partial pressures. Okay, so you're, for number 27, we're going to add the partial pressures and they will equal the total pressure. So let's say total pressure is pressure number 1 plus pressure number 2 plus pressure number 3, dot, 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 because it could be any number of pressures, all right? But that's how you do it. The sum of the partial pressures is equal to the total pressure. Number 27, the propane gas used in camp stoves really contains two gases, propane and butane. If a 770 millimeters of mercury sample of this mixture contains 0.2 atmospheres of propane, what's the partial pressure of the butane? Okay, so propane and butane. Okay, and it specifies that I want the partial pressure of butane in millimeters of mercury. So the deal with this Dalton's Law of partial pressures is that all the pressures have to be the same unit. Okay, in this case they're not, and it specifies that my answer has to be in millimeters of mercury. Well, my total pressure is already in millimeters of mercury. This is not. So I'm going to convert 0.2 atmospheres of propane into millimeters of mercury. I'm going to do it right here. I've got a little bit of room. So 0.200 atmospheres of propane. Then I'm going to use my conversion factor. I'm going to just go down my atmospheres, and I want it in millimeters of mercury. So I go back to my conversions. 760 millimeters is 1 atmosphere of pressure. Let's see. Multiply 0.2. Sorry about that. Husband keeps texting me. 0.2 times 760 divided by 1. 0.200 times 760 divided by 1. Look what I got. 152 millimeters of mercury. See, that wasn't so bad. So now I have this partial pressure and I've got my total pressure. So that's P1. So total pressure is 770 millimeters of mercury. I set my total pressure equal to the sum of the pressures. So my first pressure that I have was 152 millimeters of mercury, and that was propane, plus my butane. Sorry, I knew I was going to sneeze. Okay, and so I'm looking for my butane. Well, if it's the sum is equal to the total pressure, I just have to go, all right, 770 minus the 152 millimeters of propane, millimeters of mercury, that gives me 618 millimeters of mercury of butane. Okay, these two added together, partial pressures equals the sum, the total pressures. All right. One more combined gas law for you. Okay, remember combined gas law, P1V1 over T1 equals P2V2 over T2. A sample of unknown pressure occupies 0.766 liters at a temperature of 298 Kelvin. The same sample of gas is then tested under known conditions and has a pressure of 32.6 kilopascals and occupies 0.644 liters at 303 Kelvin. What was the original pressure of the gas? Okay, so this is our initial numbers. So the initial pressure is what I'm looking for. I don't know what that is. Liters is volume, so that's my V1. That's my T1. And look, it's already in Kelvin. Let's see, kilopascals, that is a pressure unit, so that's got to be P2. 0.644 liters is my V2. And my final temperature, it says, is 303 Kelvin. So I list out my variables. P1 equals X. I don't know what it is. V1 is 0.766 liters. T1 is 298 Kelvin. P2 is 32.6 kilopascals. V2 is 0.644 liters, and T2 is 303 Kelvin. So I'll put all of these in this formula. P1 times V1 over T1. Set that equal to P2 times V2 over T2. Okay, cross multiply and divide. So I'm going to cross multiply these. I'm going to cross multiply 298 times 32.6 times 0.644. I don't know if you can see that. Let me move it up so you can see it. There we go. So 298 times 32.6 times 0.644. That is 62.56. And I'm going to set that equal to 0.766 times 303 times P1. So P1 times 232. Then I'm going to divide both sides by 232. Divide 232. Divide by 232. And P1 equals, let's see, 62. Let me go back up here and grab this number. Divided by that number, 26.9. So how many sig figs can I have? That's 3, 3, 3, 3, 3. Okay, so 3 sig figs. 1, 2, 3. So that 5 will round that up. So instead of 26.9, your final answer, are you ready for it? 27.0 kilopascals. Okay, good luck, kiddos.